Hello, my name is Donghyun Han, a PhD student at Utah State University. I'm glad to present our work on behalf of my co-authors. Immersive analytics indicates carrying out visual analytics using immersive technologies like VR and AR. Earlier works have suggested that some visualizations could be more effective in immersive environments, helping users better understand data than in typical 2D desktop environments. Unlike the 2D desktop environments, data exploration in immersive space is accompanied by visualizations or users' movement. To provide users with better analytical task environments in immersive space, a deeper understanding of 3D user interaction techniques is essential. In this work, we evaluated 3D spatial interaction techniques in terms of their spatial working memory support. Spatial working memory refers to the ability to search and recall spatial placements of items in a given area. This ability within an information space is important to perform visual analytical tasks such as data comparison, data exploration strategy planning, and trend and anomaly detection. We first identified three 3D interaction techniques for data exploration in immersive environments. First, walking. Users can physically walk within immersive space to navigate a 3D plot. It is the most natural way of traveling because of the high biological symmetry of how humans move in the real world. Second, grab. Users can grab a 3D plot by operating a controller or hand and changing its orientation to see the plot from a different perspective. In this work, grab only allows users to rotate a 3D plot along its y-axis. Lastly, teleportation is a widely used technique in many VR applications. If a user points to a floor and activates teleportation, the user will instantly move to that location. In this work, we defined teleportable areas and users can only teleport to these predefined areas. Our research question is which 3D user interaction technique would best support users' working memory to explore 3D visualizations? To answer our research question, we designed our task based on the Corsi block tapping test using 3D scatterplot. The Corsi block tapping test is a psychological test for assessing visual-spatial working memory. For more details about the test, please see our paper. These 5 steps are the task procedure. In the beginning, participants are asked to move to a start position where an arrow mark is located. In the position, participants can see the entire scatter plot. Next is the memorizing stage. 3 out of 30 data points in the scatter plot are highlighted, and participants are asked to memorize their positions and order. Following that, participants conduct the first tapping task stage. This is a validation stage to check whether they memorize the 3 data points precisely before data navigation. Then, participants move to the next position or change the orientation of the chart using one of 3 interaction techniques. In the new view perspective at last, they conduct the second tapping task by recalling the 3 data points in the same order which they saw in the memorizing stage. We first conducted a VR study. A total of 18 participants were recruited. It took about 45 minutes. The study was conducted with BioPro 2 with its wireless setting. 3 independent variables are 3D interaction techniques, view transition angles, and tapping orders. We have 4 dependent variables of task distance error, interaction time, subjective performance, and motion sickness. Study results were analyzed by using within-subjects ANOVA at the 95% confidence level. A post-hook analysis was performed using Tukey's HSD at the same 95% confidence level with a Bonferroni adjustment. Regarding distance error, we found no interaction effect, but three main effects were disclosed. We found that walking and grab were statistically more accurate than teleportation, while walking and grab showed no difference. In addition, a smaller view change had a smaller error, and the first tap had a statistically smaller distance error than the second and third taps. We found a significant interaction effect on interaction time between technique and view transition angle. At the 90-degree transition condition, walking had a faster interaction time than grab and teleportation. However, at the 180-degree transition condition, no statistical difference between walking and teleportation were disclosed. In this condition, grab showed the worst performance. The participants rated that teleportation required much smaller physical effort to navigate 3D scatter plots than walking. We discovered no difference between teleportation and grab, nor between grab and walking. In terms of self-success, walking and grab had higher scores than teleportation. Interestingly, no significant difference in motion sickness was found between the interaction techniques. We next conducted an AR study using Microsoft HoloLens 2. 10 participants were recruited. The study design, tasks, and analysis methods were basically identical to the VR study. In this study, however, only walking and grab were evaluated except teleportation. We found no interaction effect on distance error. We found main effects on interaction technique and view transition angle, but not tapping order. We found that walking is statistically more accurate than grab. Similar to the VR study result, a smaller view change has a smaller error. Regarding interaction time, we found no interaction effect, but two main effects on the interaction technique and view transition degree are disclosed. Walking had a significantly shorter interaction time than grab, and the 90-degree view change condition had a short interaction time than its 180-degree condition. We found no significant difference on the subjective measurements between walking and grab. After the VR and AR studies, we compared their results using a non-null hypothesis statistical test, focusing on the sample mean and bootstrapped 95% confidence interval. We expected that VR will have smaller distance error than AR because VR users could focus more on 3D plots than AR users due to their background characteristics. However, our results show that AR has statistically smaller errors than VR. The interaction time in VR were much faster than AR for both walking and grab. Here are brief summaries of our findings. Walking outperformed other user interaction techniques in both AR and VR. Larger transition movements impair spatial memory performance. Teleportation supports spatial memory the least in the VR study, but many participants noted that it is the simplest way to explore VR environments. The participants in AR show better spatial memory performance than the participants in VR. 3D user interaction techniques have comparable motion sickness. Highlighting or annotation techniques would help users in low-level data exploration in immersive environments. In this work, we evaluated the interaction techniques in terms of their visual walking memory support in VR and AR. We find that walking supports spatial memory the most, and grab follows. Walking and grab are suitable for exploring data in single 3D charts, whereas teleportation might be helpful to move to other charts in immersive spaces. In real scenarios, however, there are various conditions about data size, data distribution, as well as chart size. In addition, users might want full 6 degrees of freedom navigation around 3D chart. Examining technique effects for these scenarios are future work. This is all for our presentation. Thank you for your attention.